Alrighty, here we are with the second set, or second video for this. We're going to go through the parallel portion of the circuit. So the last time we went through these guys, we were going through the series. Now we're going to go through RL circuits, just in the parallel configurations. Like I said, these are going to be following the same format as before. We're going to go through a couple of these circuits and basically go through and solve everything. And if you do have questions, like always, please feel free and reach out, and I will do my best to answer your questions as they come up. All right, so the first thing that we're going to do is we are going to have our circuit. So we're going to have a resistor and an inductor in parallel. So we've got L1, he is at 22 millihenries with a winding resistance of 150 ohms. We have R1, who is 300 ohms. And our source is putting out 17 volts peak at 1741 hertz. Things we're going to be looking for is we want to find the reactance for L1. We want to find the total impedance of L1. And we want to find the impedance total of the entire circuit. After that, we're going to find our current total. We're going to find the current through branch A and the current through branch B. Let me just label these right there. And of course, as always, our ground is down here. So the first thing we need to do is we need to solve for the inductive reactance of the circuit. So remember that inductive reactance is solved as 2 pi times the frequency times the inductance itself. So the inductance of inductive reactance of inductor 1 is as follows: 2 pi times the frequency, which is 1741, times the inductance, which is 22 milli. This total comes out to be 240.659 ohms at an angle of 90 degrees. Now we need to find the total impedance of this inductor, because remember we have the winding resistance. So the total impedance of inductor 1 is the 150 plus J of 240.659. Go away. Okay, so now we need to take this value and we need to convert it into polar, because we're going to be using it to find all of our impedances. Our total impedance has to be in parallel, so we're going to be doing some division. So we need to convert this guy to polar. So when we do that, the total inductance for L1 comes out to be 283.578 ohms at an angle of 58.065 degrees. Now, since these guys are in parallel, our impedance formula for the total of this is going to be 1 over R1 plus 1 over the impedance of inductor 1. So again, we can take this guy and we can convert it to admittance to get rid of the reciprocals for at least the first part, and then make it easier to solve. So here we have 1 over 300 at 0. And then here we have 283.578 at 58.065. So we do those reciprocals, and we end up with 3.333 millisiemens at 0 degrees plus 3.526 millisiemens at negative 58.065 degrees. Now, because we're adding, we have to convert both these guys into rectangular so we can add their similar parts. And when we do that, this one converts quickly to 3.333 milli plus J of 0. And this one converts to 1.865 milli minus J of 2.992 milli. So now that we have that value, we're going to add our similar terms together. So our admittance total turns into 5.198 minus J of 2.992 milli. And now we want to take this value, convert it to polar because we have to take the reciprocal again. So this turns into 5.998 milli at an angle of negative 29.925 degrees. Now we take the reciprocal of both sides again to convert this back into our impedance. And when we do that, we get 166.722 at an angle of 29.925 degrees. And remember, that's all in ohms. The admittance, remember, is in Siemens. So there is our total impedance for the circuit. Now, to continue on, we need to find the current total through this circuit. So our I total is equal to V total divided by our impedance total. So we have 17 volts peak at 0 degrees. We divide that by the impedance total that we got. So it's 166.722 at an angle of 29.925. Our current in this instance comes out to be 101.966 milliamps at an angle of negative 29.925 degrees. Now the last part that we need to do is we need to be able to solve for the currents. And since the resistor and the inductor are the only things in parallel with each other, the voltages are going to be the same. And those things are also in parallel with the source. So all the voltages are going to be the same at 17 volts. So now current A through branch A is going to be equal to the voltage total divided by the impedance of branch A. So we start out with 17 volts peak at 0 degrees, and we divide that by 300 ohms at 0 degrees. So in this instance, the branch current for A is going to be 17 divided by 300, which is 56.667 milliamps at an angle of 0 degrees. And then IB is going to be the same steps, the voltage total, because that's what's in parallel with the impedance in branch B. And in this case, the impedance of branch B is equal to the impedance of inductor 1, because that's the only thing that's in the branch. So we take our 17 volts peak at 0 degrees, we divide that by the impedance that we got from our inductor, which was 283.578 at an angle of 58.065. We run this through our calculator, and the current comes out to be 59.948 at an angle of negative 58.065 degrees. Now we can take these two together, and we can convert them both to rectangular to double check, and add them together, IA and IB, and that'll equal our I total. I'm not going to show that in this video, as we have done this quite a lot, and it's just used simply as a double check. So that's it. That's all we have to do to solve parallel circuits. When they are just simply a resistor and an inductor, they're very easy to do, just like the capacitors were. But this will give you kind of a taste and an introduction to solving these parallel circuits. So now, let's move on to our next equation, next circuit. So this one, here's our source. We have a resistor, and that is in parallel with another inductor. Our ground is down here. This is point A. This is point B. We have 30 volts peak coming in, and we have 1484 hertz. So our inductor is 1.6 henries. with 295 ohms of winding resistance, and our resistor is 15 kilo ohms. So we have R1 and we have L1. So the things we're going to find, the inductance, the inductive reactance of L1, our total impedance of L1, and our total impedance of the circuit. We want to find our current, we want to find the current through branch A, and we want to find the current through branch B. Now again, to find X of L is 2 pi times the frequency times the inductance. So XL of inductor 1 is 2 pi times 1484 times 1.6 henries. So the X of L1 is going to be equal to 14,919 ohms at 90 degrees. So there is our first value. Now the next one you need to find is the impedance total for our inductor. So we have 295 plus J of 14,919. We want this guy in polar. So the total impedance of inductor 1 is going to come out to be 14,922 at an angle of 88.867 degrees. So now that we have the impedance and we have the resistor, we don't have to do anything to that. Now we can solve for the total impedance of our circuit. So again, the total impedance, and since they're in parallel, we're going to use the reciprocal method. Okay, so then we have our admittance to get rid of the top reciprocal value. So we're left with 1 over 15K at 0 plus 1 over almost 15K at 88.867. This comes down to be 66.667 micro at 0 plus a 67.015 micro at a negative 88.867. Now we're adding, so we're going to convert these guys into rectangular. So this is going to be 66.667 micro plus J of 0. And the next value is going to be 1.325 micro minus 67.002 micro. And then we end up with a total of 67.458 micro minus J of 67.002 micro. Now we're going to take this value, we're going to convert it back into polar because we're going to be dividing it by 1, taking the reciprocal, so it needs to be polar to divide. So the admittance total of this circuit comes out to be 95.458 micro at an angle of negative 44.58 degrees. Now we take the reciprocal of this guy to give us our impedance and to put it back into the form that we need. This comes out to be 10,476 ohms at an angle of 44.58 degrees. So now remember what I said, as these guys are coming closer and closer to each other, so in this case if you look, the susceptance and the conductance of each of these guys, so this is conductance of the real part, the imaginary, the opposite of that is called susceptance, remember. These are almost equal, so since they're almost equal, we should be approaching the 45 degrees, and which we do. We get really close, and if we were to round it off, yeah, we would end up with the 45 degrees. So we now have the total impedance of our entire circuit. Now we're going to take our current total. So we take the voltage total divided by our impedance total. So we get 30 volts at 0 degrees, and we're going to divide that by the 10,476 at 44.58 degrees. The current total comes out to be 2.864 milliamps at an angle of negative 44.58 degrees. Now, the last two parts that we need to solve for is the current through branch A and the current through branch B. So the current through branch A is equal to the voltage total, since that's what's in parallel with the impedance of A. So we have 30 volts peak at an angle of 0 degrees divided by all the impedance that's in A, which is just the 15 kilo ohm resistor at 0 degrees. So the current through A is equal to 2 milliamps at 0 degrees. And now we're going to take the current through B. Again, it's equal to the voltage drop divided by the impedance of B. And remember, since all that we have in B is just the impedance of inductor 1, makes it really easy. So we have 30 volts peak at 0 degrees, and we divide that by the impedance, which we get 14,922 at 88.867 degrees. And the current we get through B is equal to 2.01 milliamps at an angle of negative 88.867 degrees. And that's one of the cool parts about these guys too, is you'll see these values coming across. Now when we hook up our scope and we go to measure these guys, this is what's one of the cool things about this, is so we have this current going through our IA going through that branch, we have IB going through that branch, but when we measure it, we're going to be measuring one, the voltage across each of these components, and we're also going to be measuring the source. So if we look again, just as a quick double check, we can work this backwards. We take our current times our resistance or our impedance, multiply those together, we're going to get 30. So if we look at B for a moment, if we have this current, so we have IB times the impedance of inductor 1, so we have 2.01 milliamps at negative 88.867 degrees. We're going to multiply that by the 14,922 at 88.667 degrees. We multiply those two across, we're going to get 30 volts. We add these two together, so we have a negative 88 and we have a positive 88. That's going to net us 0. So even we can go back and double check and prove that yes, we're still going to get everything that we have. The current and the voltage are going to be out of phase, but combined together, the impedance and the current are out of phase, but they're almost 180 degrees out of phase, which means they're going to come back in and reach a 0 value. So this is kind of a quick little double check to make sure you get everything back, and it should all work out just fine. And so there is our final answer of IB. And with that, there is two examples of parallel. Parallel by itself is actually pretty easy when we do this method. Now, the other way you can do is you go through these. So remember, when we come back up here to finding our impedance, this, using the reciprocal method, is just one way we can do this. Remember, we do have another method, and if you guys want to try it, so remember, we can always use the reciprocal to find things in parallel. But remember, we have one special rule that if we have two branches, it's the product over the sum. So in this case, so if we're talking about an impedance for a parallel branch, and we have two branches only, we can also use the impedance of branch A times impedance of branch B, and divide that by the impedance of branch A plus the impedance of branch B. So we do have this other special case if you want to use it. So in this case, you'd have to have both the impedances in polar and rectangular. But hey, look, we already have those in polar and rectangular. We have to solve it rectangularly to get the equation to solve for polar. And when it's just the resistor, it's really easy. So you can do both of these directions to solve for the total impedance either way if you want. This one might have a few less steps, a few less conversions. But either way, like I said, you can use either one. This one is just straightforward. You can have any number of parallel branches. so we can do them all at once. If we use the special case, we can only do it 2 branches at a time. But you do have those options if you wish to use them. If you guys want me to go over those again with you more, I'm more than happy to, and we can run through a problem using this and kind of go from there. But again, if you guys do have any questions, please feel free and reach out, and I will answer them to the best of my ability, and we will get you guys set up and squared away. And so with that, that is the parallel circuits. The next video I'll have up and going is the series parallel circuits for RL configurations.